This is SpaceTime, Series 20, Episode 68. Coming up on SpaceTime, a bizarre-looking white dwarf, the first ever X-rays detected from a thermonuclear supernova, and a new look at how the Earth was formed. All that and more coming up on SpaceTime.
Welcome to SpaceTime with Stuart Gary.
Astronomers have identified an unusual type of white dwarf star, which may be the leftover remains from a recently discovered new type of sub-luminous supernova. The findings, reported in the journal Science, also support the idea that there's more than one way of generating these powerful cataclysmic stellar explosions. The white dwarf, known as LP40-365, is far smaller than other white dwarfs. It's also moving across the sky at an incredibly fast rate, in fact greater than galactic escape velocity. That's incredibly fast compared to most other stars. And it doesn't end there. This white dwarf also has a really strange composition, different from most other white dwarfs ever examined. One of the study's authors, Professor Lilia Ferrario from the Australian National University, says the white dwarf's unusual characteristics may help scientists determine its origins. A white dwarf is the stellar corpse of a dead sun-like star. Stars shine by fusing protium hydrogen in their cores into helium. Now, eventually, stars will run out of hydrogen in their cores. They'll then begin fusing all that helium they've made into heavier elements such as carbon and oxygen. The thing is, helium fusion takes more energy than hydrogen fusion, so the star gets a lot hotter in its centre and it expands. Because the star's visible surface is now further away from the stellar core, the visible surface becomes cooler and therefore redder, in the process turning the star into a red giant. While really massive stars fuse carbon and oxygen into progressively heavier and heavier elements, stars like the Sun aren't big enough to do that, and so once their core is fused into carbon and oxygen, these stars die. The huge amounts of heat generated by the stellar core pushes away the star's outer gaseous envelope in a series of strong pulsations, caused by nuclear burning shells around the degenerate core that eventually eject the stellar envelope, which forms a spectacular-looking planetary nebula. What's left behind is the white-hot stellar core, a super-dense ball of oxygen and carbon about the size of the Earth, known as a white dwarf, which will slowly cool over the eons. Now, if the white dwarf just happens to be in a close binary orbit with another star, then the white dwarf, being really dense, will gravitationally draw material off this companion star. This process can continue until the white dwarf draws enough material off the companion star to reach a critical mass around 1.44 times the mass of the Sun. It's a figure known in astronomy as the Chandrasekhar limit. Once a star reaches this Chandrasekhar limit, the added mass causes the gravitational collapse of the white dwarf, beyond the electron degeneracy which usually prevents further collapse due to the Pauli exclusion principle, which stops two electrons or other fermions from occupying the same quantum state. This triggers a runaway fusion reaction, causing the white dwarf to explode as a thermonuclear or Type 1a supernova. But that's not the only way thermonuclear supernovas can occur. Another way of reaching the Chandrasekhar limit would involve the merger of two white dwarfs into a single star. Now, either way, the white dwarf is destroyed in a Type 1a supernova, an explosion so catastrophic that it can briefly outshine an entire galaxy. Because all Type 1a supernovae are thought to explode with about the same mass and energy, as I said, roughly 1.44 times that of the Sun, they all exhibit roughly the same luminosity. And that makes them really useful to astronomers as standard candles to measure cosmic distances across the universe. It's a bit like looking at a row of streetlights along a road. You can sort of get an idea of how far away each streetlight is by how bright it appears compared to the others. And this quality has made Type 1a supernovae not just important as cosmic distance markers, but also for measuring the accelerated expansion of the universe, and therefore the discovery of dark energy, a force which will determine the ultimate fate of the universe. Astronomers are still debating whether white dwarf mergers or white dwarfs feeding off companion stars are more likely to produce Type 1a supernovae. And that's where white dwarf LP40-365 comes in. This object is so unusual in terms of its size, composition and movement across the sky, the authors think it may be a surviving remnant from a Type 1a supernova event. The explosion destroyed most of the original white dwarf and flung what's left across the galaxy, where our authors decided to study it. The research indicates LP40-365 may be the result of an unusual type of sub-luminous thermonuclear supernova which exploded between 5 and 50 million years ago, tens of thousands of light years from Earth. First identified in 2013, these sub-luminous supernovae have been named as Type 1aX. That's because they look like Type 1a supernovae, but they're far less powerful explosions, which don't completely destroy the progenitor white dwarf. Type 1aX supernovae are thought to occur when the material accreting onto the white dwarf is helium. Ferrario says finding helium on a white dwarf is not per se all that strange. In fact, it's quite normal. But the presence of other elements like oxygen, neon, sodium, magnesium, aluminium, silicon and some iron is what makes this particular remnant so interesting.
This is a very interesting object because we found out that it is quite low mass white dwarf, so it's a very small star, but it has a very unusual chemical composition and it has an extremely high velocity. So it is zimming around our galaxy.
How low mass is low mass?
In terms of the Sun, I would say that it is about a seventh of the mass of the Sun. It's about 0.15 times the mass of the Sun.
Also, its chemical composition is very unusual. That must tell you some clues about what's happened to it.
Well, yes, because normally, since the age of the universe is quite finite, we know where it is about 13.7 billion years, then this means that you cannot have low-mass stars that have had a chance to evolve up to the stage of white dwarf.
No red dwarf has died yet.
No. The universe is just too young for that. We have to wait for a long, long time before red dwarfs can evolve and become a white dwarf. So at most, we would have the stars that are as massive as our Sun have had time to evolve to the white dwarf stage. So this guy is extremely light, so it's not possible. So something happened to it. So we know for sure that it must have had a companion at some stage, but a companion alone is not sufficient because why would it been traveling at this speed? I mean, it looks like it has been ejected from some phenomenon, from something that happened at some point.
And the most likely explanation for that, of course, is either it's being gravitationally kicked out by an interaction with something else, either another star or a black hole, or alternatively, it's been affected by some sort of a supernova event.
Yes, that's right, because it is possible to acquire very high speed for a range of reasons. But in this instance, we have figured that it couldn't have happened via interaction with, for instance, the galactic center, the galactic center.
Sagittarius A star.
But this is not the case for this object. This object has definitely been ejected by supernova explosion. So what we had was initially a white dwarf, but that was much more massive than this guy here. So it was accreting from a companion star, which means that it was devouring its companion. And when enough mass was dumped onto the surface of this white dwarf, it reached a limiting mass, which is known as the Chandrasekhar's mass limit. And then there was an enormous explosion and a thermonuclear runaway. And so this star exploded, but something was left behind. So this piece of shrapnel was ejected at very high speeds from the center of the explosion, and it has been traveling for millions of years in the galaxy until it reached the neighborhood of the solar system, so we could see it.
And you guys are referring to the supernova event as a Type 1aX.
That's right, yes. This is just a type of sub-luminous supernovae because, as you know, supernovae Type 1a are used as a standard candles to measure the accelerating expansion of the universe. And the good thing about this supernovae type 1a is that if they follow a certain number of characteristics, then we know that more or less their brightness is always the same. But then there are many other subclasses of supernovae type 1a, and they take many, many different names. And for whatever reason, they are not quite as luminous as the bona fide supernovae type 1a. So what happens is that maybe the white dwarf wasn't quite as massive as a Chandrasekhar mass white dwarf, or perhaps the explosion occurred in a slightly different manner, or perhaps something was left behind, like in this instance. The problem is that we don't really know what triggers the explosion yet. So even many aspects of the explosion physics is quite unknown.
Now, you were saying earlier that the chemical composition of this star was very different as well.
What happens is that usually when we looked at a white dwarf, we just see in the vast majority of cases, what we see is just a very compact, very heavy object with an atmosphere, which is a hydrogen mostly. Sometimes we can see helium white dwarfs, and sometimes you also can see white dwarfs that have been polluted by other elements. But in this instance, what you have is something that is quite different. It has the characteristics of what we call the carbon-oxygen white dwarf, but the elements that we see on its surface are quite different from what we would expect to see. When we study a star, we can study only what we see at the surface because we study the spectrum of a star. So it is the radiation that goes from the deep interior, and then it transfers through the atmosphere of the star, and then it reaches us. So what's inside a star, we can just infer it by doing some theoretical studies. In this instance, what we have found out is that there are quite a few spectral lines of sodium, magnesium, and then we also were able to see lines of oxygen, aluminum, silicon, etc. These elements are not normally found on the surface of just the standard white dwarfs, particularly not if they are low mass like this one.
An unusual looking white dwarf.
Yes, very unusual.
Must provide a fascinating subject for study.
Yes, I'm sure that many other astronomers will have a look at it. Yes.
Astronomers aren't sure of the age. They've put it between 5 and 50 million years that the event took place. How do astronomers work that out?
What we did was, again, to do some theoretical modeling for this object, but it is really hard because it is such an unusual object that it's just like studying a completely different animal. It's just like if you discover an animal that doesn't belong to any kingdom and you just try to figure out where it comes from, what it is. So that's why our errors on the age of this star is quite large. So we know that it is for sure, it's older than 5 million years, but it could be as old as about 50 million years. So we can't really give it a precise age.
How do you determine that it's older than 5 million years?
We just have looked at models for normal white dwarfs, and then we just had to extrapolate from these models and just to try to find a fit for this unusual white dwarf. We start from something that we know, and then we just try to adjust our modeling techniques in order to fit something that we have never seen before.
And how do you determine the age of a star? Is it the chemical composition and how that's evolved?
Mostly we look at things like physical parameters, like the temperature of the white dwarf. It is are all inferred parameters. Again, we study its distance by looking at its luminosity, and then we derive a certain temperature, and we derive a certain mass, and from mass then the radius, and so on. And once we have all these various quantities, we can derive what the age of the star is.
Are you able to see the star at all in any detail, or is it just a single point light source?
Well, it's actually quite bright because it's not a star that had never been seen before. It had already been catalogued. The problem is that it was something that people must have misunderstood for something else. So people never paid much attention to it, but it is quite bright. It is quite surprising that nobody had done any serious studies before we did.
Is this telling us something new about the structure of white dwarfs?
Yes, we can definitely learn something more about white dwarfs, and we will have some information on, for instance, the minimum mass that these stars can have and what their structure is and so on. But what is more important is that it gives some weight to one of the theories that have been brought forward to explain the origin of supernovae of type 1a. That's the most important part of it. We don't really know what their precursors are. So there are two main theories. One theory says that these incredible explosions happen because two white dwarfs merge. And in the other camp, the other theory says what happens is that we have a white dwarf star that is eating up its companion star, so a lot of mass falls onto the white dwarf, and then you have this supernova explosion. In this instance, what we can say is that this surviving remnant of a supernova explosion gives weight to the theory where you have a white dwarf that is eating up its companion. And this is called the single degenerate scenario. The reason is that there is only one star that is degenerate, while instead in the double degenerate scenario, you have that both stars are degenerate. They are both white dwarfs.
That's Professor Lilia Ferrario from the Australian National University. And this is Space Time. I'm Stuart Gary. Astronomers have for the first time detected X-rays coming from thermonuclear or type 1a supernovae. As we mentioned earlier, type 1a supernovae have helped scientists develop their current understanding of the universe, but researchers are still in the dark about many of their features. And these new findings, reported in the monthly notices of the Royal Astronomical Society, are raising further questions about how these supernovae are formed. A few years ago, scientists began finding a group of type 1a supernovae carrying strange optical signatures which suggested that they were carrying a very dense cloak of circumstellar material around them. Such dense material is normally only seen from a very different type of supernova called a type 2 or core collapse supernovae. These occur when stars much more massive than the Sun explode at the ends of their lives, resulting in the formation of either a rapidly spinning neutron star, a pulsar, or a black hole. It's theorized that the ejected mass of the progenitor star to a core collapse supernovae collects around the star, and then when the star goes supernova, the explosion sends a shock wave hurtling at supersonic speeds into this dense cloud of material, producing a shower of X-rays. Because of this, scientists regularly see X-rays coming from type 2 supernovae, but they've never previously detected them from type 1a supernovae. And that's where this new study comes in. When astronomers studied a type 1a supernova known as SN2012Ca using NASA's Chandra X-ray Observatory, they detected X-ray photons. One of the study's authors, Associate Professor Vikram Dwarkadas from the University of Chicago, says other type 1a supernovae with circumstellar material were thought to have similar high densities based on their optical spectra. However, scientists had never previously detected them in X-rays. Mind you, the amount of X-rays actually monitored was fairly small. Just 33 photons in the first observation a year and a half after the supernova exploded, and another 10 about 200 days later. Still, it suggests a density at least 1 million times higher than what astronomers thought would be the maximum around a type 1a supernova. And the reason that's so surprising is that it was thought that the white dwarfs which produce type 1a supernovae don't lose mass before they go supernova. Because of this, the usual explanation for circumstellar material being found around what becomes a type 1a supernova is that it probably originated from the companion star in the system. However, the amount of mass suggested by these observations was very significant, in fact far larger than what one would expect from most companion stars. Astronomers don't know how much circumstellar material could form in such a system. Even the most massive stars don't have such high mass loss rates on a regular basis. And that's therefore raising questions about how these spectacular explosions are formed. More studies looking for X-rays and even radio waves coming from these anomalies could therefore open up a new window to understanding the mysteries of type 1a supernovae. You're listening to Space Time. I'm Stuart Gary. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook just go to www.facebook.com/Spacetime with Stuart Gary. New geochemical research indicates existing theories into the formation of the Earth just may be a little bit wrong. And before you say it, in this case, wrong is not an absolute. As made famous in the Big Bang Theory, it's a little wrong to call a tomato a vegetable, it's very wrong to call it a suspension bridge. The new claims on Earth's formation are based on experiments looking at how the element zinc relates to sulphur under the conditions present at the time of Earth's formation 4.6 billion years ago. The findings, presented to the Goldschmidt Geochemistry Conference in Paris, indicates that a substantial quantity of zinc should have sunk down to the Earth's core, and that contradicts previous hypotheses which thought there wouldn't be any there. The findings imply that the building blocks of the Earth are somewhat different to what had been previously hypothesized. To reach their conclusions, researchers melted mixtures of iron-rich metals and silicate compounds containing zinc and sulphur at temperatures of up to 4,100 Kelvin and pressures of up to 80 gigapascals to experimentally simulate core mantle differentiation at the time of Earth's formation. They then measured how these elements were distributed between the core and mantle of their experiments. When they fed their results into computer models of the Earth's formation, they found that none of their existing models could sufficiently reproduce the sulphur-zinc ratio of the present-day mantle. This means that the current estimates of Earth's composition, including its core, need to be modified. And that means the way the core and mantle, and therefore the planet itself formed, will need to be revised. One of the study's authors, Brandon Mann from the Institute of Global Physics in Paris, says most theories are based on Earth being formed from only two types of stony meteorites, these being Ci or C1 chondrites and E or enstatite chondrites. However, the new research indicates that the Earth needs to have formed from a more sulphur pool source in terms of its geochemistry. And the best candidate for this material would be metal-rich CH chondrites. CH chondrites were first classified in 1985, and only a few dozen examples have been identified. They're rich in metallic iron and poor in easily vaporized elements, and all that indicates formation at very high temperatures. But they also contain a few percent of water-bearing minerals, and that paradoxically indicates low temperatures. Now, all this means that CH chondrites, much like the Earth itself, have very complex formation histories, which has given them features of both extremes, hot and cold. If the results are correct, it means that planet Earth's building blocks must be far more exotic than previously thought. Existing theories for the Earth's formation are largely based on geochemistry. And one of the major geochemical clues for Earth's formation lies in the way elements such as zinc and sulphur in meteorites are associated in a relatively well-known ratio. Meaning that if you know the amount of zinc in a meteorite, you can pretty well estimate fairly accurately the amount of sulphur there. So, the authors decided to test if that ratio was the same for the growing Earth as what it is today by using various possible source materials. They found that under conditions similar to those estimated when the Earth formed, zinc had a tendency to be distributed between the Earth's core and mantle somewhat differently to what was thought, with heaps more zinc bound up in the Earth's core. Based on previous models, if there's more zinc in the core, then by association there must be more sulphur in the core as well, in fact much more than current models suggest. Most leading estimates cap the amount of sulphur in the Earth's core at around 2%. If true, then using most known meteorites as a source for material for the Earth puts the sulphur-zinc ratio in the mantle way up above current accepted values, because too much sulphur ends up in the mantle. Now, what all this means is that planet Earth could not have been made from many of the solar system materials previously proposed as source material. However, if the Earth's building blocks were instead based on CH chondrites, this would give the Earth a fairly similar composition to what's actually seen today. I'm Stuart Gary. This is SpaceTime.
For you, the listeners of SpaceTime with Stuart Gary, Audible is offering a free audiobook download with a free 30-day trial to give you the opportunity to check out their service. Some suggestions from us would include bestsellers such as Breaking the Chains of Gravity, the story of spaceflight before NASA by Amy Shiratitle, Astrophysics for People in a Hurry by Neil deGrasse Tyson. Or maybe science fiction is more your thing. How about Earth Shadows by Daniel Aronson? Or Not Alone by Craig A. Falconer. So many great books, no matter what your taste. Over 180,000 titles to choose from. And no need to rush. Not only do we give you a free book, but you have 30 days free trial to browse to your heart's content. To download your free audiobook today, go to audibletrial.com/spacetime. Again, that's audibletrial.com/spacetime for your free audiobook. Or click on the banner link at spacetimewithstuartgary.com.
SpaceX has continued its rocket launching blitz for 2017, with Taiwan's Formosat 5 blasting into orbit aboard a Falcon 9 rocket. The flight from the Vandenberg Air Force Base in California successfully placed the 475-kilogram remote sensing satellite into a 720-kilometre high low Earth orbit.
Falcon 9 is configured for flight. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Lift off the Falcon 9. Drop AVIRC and GNC. Procedure 3.170 for post-launch flight operations.
Stage 1 propulsion is nominal.
GC, please move to post-launch pad operations and secure the pad on PadNet 8.
Copy.
Falcon 9 has lifted off from the Space Launch Complex 4 pad with the Formosat 5 spacecraft attached. In about 18 seconds, we're going to hit max Q, which is maximum aerodynamic pressure. That is the point at which the aerodynamic pressures on the vehicle are the highest in the set. Now, in about a minute, we're going to have three major events coming up in rapid succession. Main engine cutoff, that is where all 9 engines on the first stage are going to shut down. Up next will be stage separation. That's the point at which stage 1 will separate from stage 2. Stage 1 will fly down to the drone ship. Stage 2 will continue on to space. And from there, immediately after, we're going to see second engine start. That is going to be the ignition of the Merlin vacuum engine, which is the upper stage engine on stage 2. MVAC engine chill has begun. It's looking really good.
Here we go.
Great news. We've had successful main engine cutoff, successful stage separation, and MVAC has ignited. The Merlin vacuum engine has ignited. The grid fins have just deployed. The first stage's entry burn is going to begin. That's where 3 of the Falcon 9 engines are going to reignite and slow down the first stage as it re-enters the Earth's atmosphere. If we don't slow down, we'll burn up on re-entry, so we have to slow the vehicle down. That's going to be about a 39-second burn.
Stage 2 probably stop.
We're hearing that stage 2 is nominal. Everything is looking good. The trajectory is looking good. Prop is nominal. So while stage 1's entry burn is going to be burning, we're going to see the stage 2 main engine, the Merlin vacuum engine, is going to shut off. After the entry burn, there's going to be about a 50-second period where there are no engines burning, and at which point, after that concludes, the stage 1 landing burn is going to begin. That is where the center engine, E9, for Falcon 9's first stage, is going to reignite, and that is going to slow the vehicle down to 0 velocity and hopefully put it in a position to land right up on Just Read the Instructions, our West Coast drone ship. Now, if we're successful here, this will be the 15th successful recovery of a Falcon 9 first stage. MVAC continues to be performing very well. Everything is nominal on stage 2. We're just under, it's before that entry burn is going to begin on stage 1. And again, during that entry burn, Stage 2's Merlin vacuum engine will shut down. This is a short flight. We're not going to have an extended duration coast. Only 2 minutes after SECO, after that Merlin engine, that vacuum engine on stage 2 shuts down, only 2 minutes afterwards, we're going to deploy the Formosat 5 spacecraft onto orbit.
Stage 2 AMTS has saved.
coming up on that entry burn any minute, any second now, and the Merlin vacuum engine on stage 2 continues to perform beautifully.
Stage 1 entry burn has started.
That entry burn has started on stage 1. It's going to last 39 seconds.
PFC go.
And we have second engine cutoff over on stage 2, and the entry burn appears to have ended on stage 1.
Stage 1 entry burn shut down.
And we're getting confirmation that we have a good orbit for stage 2. This is very good news. That is the primary mission, and getting to that orbit is the whole goal of today. Coming up in just under 2 minutes, we should see the deployment of the Formosat 5 spacecraft into low Earth orbit. Now the landing burn should be starting. That burn's going to last 33 seconds.
Stage 1 is transonic. Chip AOS.
That landing
Stage
burn
1
has
landing burn has started.
The drone ship in the view.
Landing legs are deployed.
There we go.
Falcon 9 is landed.
Falcon 9 has landed on just instructions. This is the 15th successful landing of Falcon 9. Now there's still the main mission, payload deploy, coming up any second now. And we've had a successful deployment of the Formosat 5 spacecraft into low Earth orbit. And with that brings Falcon 9's job to a close today.
The Republic of China's National Space Organization's Formosat 5 is equipped with a remote sensing imager payload, providing multispectral and panchromatic imaging of the Earth's surface using a 45-centimetre Cassegrain reflector telescope, providing a resolution of 4 metres. The spacecraft also carries an advanced ionospheric probe designed to study plasma in the ionosphere using a planar Langmuir probe, a retarded potential analyzer, an ion trap, and an ion drift meter. The instrument package will allow scientists to study Earth's ionosphere, recording the composition and density of plasma, as well as the velocity and temperature of ions and electrons. The Formosat 5 spacecraft carries enough fuel to remain operational for at least 5 years. The mission was the 12th launch this year for SpaceX and the Falcon 9. The next Falcon 9 launch is slated for the Kennedy Space Center on September 7, with the first SpaceX launch of an X-37B military space shuttle on the classified OTV-5 mission for the United States Air Force. This is SpaceTime. I'm Stuart Gary. And time now to take a brief look at some of the other stories making news in science this week with the Science Report. And a new study claims older lesbian, gay and bisexual or LGB people are more likely than older heterosexuals to suffer chronic health conditions, experience sleeping problems and drink excessively. The research, reported in the American Journal of Public Health, also found that in general, older LGB adults were more likely to be in poorer health than their straight counterparts, specifically in terms of higher rates of cardiovascular disease, weakened immune systems, and lower back or neck pain. LGBs were also at greater risk of adverse health behaviours such as smoking and drinking excessively. The 2-year study is based on research on 33,000 heterosexual and LGB adults over the age of 50, taken by the CDC, the US Centers for Disease Control and Prevention, which had found noticeable health disparities between LGB and heterosexual adults. Previous studies had already linked poorer health outcomes for LGB people to greater discrimination and victimisation. The new study found both disability and mental distress were significantly more prevalent among lesbians and gay men than among their bisexual counterparts. And strokes, heart attacks, asthma, arthritis and lower back or neck pain affected significantly greater percentages of lesbian and bisexual women than their heterosexual counterparts, with some 53% of lesbians and bisexual women experiencing lower back or neck pain compared to less than 40% of heterosexuals. The study also found that nearly 7% of gay and bi men, compared to just 4.8% of straight men, suffered chest pain related to heart disease. Also, more LGB people reported weakened immune systems, about 17% for women and 15% for men. That compared to just 10% for straight women and 5% for straight guys. The study also found that lesbian and bisexual women were up to 2 times more likely to engage in adverse health behaviours such as excessive drinking. Paleontologists have discovered a new species of sauropod dinosaur in southwestern Tanzania. Sauropods are those dinosaurs that look like the Flintstones' pet Dino, with an elephant-like body and legs, with a really long neck and small head at one end, and a very long tail at the other. The new discovery, reported in the Journal of Vertebrate Paleontology, is of a type of sauropod known as the titanosaur. The fossils were found in 70 to 100 million-year-old rocks dating back to the Cretaceous period. Titanosaur fossils have been found worldwide, but they're best known from South America, and fossils from this group are rare in Africa. The discovery by paleontologists from the Field Museum of Natural History in Chicago and Brisbane's James Cook University shows that the new dinosaur is more closely related to titanosaurs from South America than to any of the other species currently known from Africa or elsewhere. The new dinosaur species has been named Shingapana songwensis, derived from the Swahili term Shingapana or wide neck, and the fact that they were discovered in the Songwe region of the Great Rift Valley in southwestern Tanzania. During the tectonically active Cretaceous period, southern Africa lost Madagascar and Antarctica as they split off to the east and south, followed by the gradual northward unzipping of South America. Northern Africa, meanwhile, maintained a land connection with South America, but southern Africa slowly became more and more isolated until the continents completely separated some 95 to 105 million years ago. A new study has found that the emotional facial expressions of people can influence how people perceive an odour. The findings, reported in the journal Scientific Reports, shows how expectations can influence perception. The work's based on functional magnetic resonance imaging of how the brain processes the combination of emotional information and odours. Researchers had their participants look at a picture of a person with either a happy, neutral or disgusted facial expression. Afterwards, they had them rate one of 12 different odours. And amazingly, the picture of the facial expression really did affect the way odours were perceived. Participants rated the valence of a scent higher when they first saw a happy face, while they rated the valence as poorer if they had first seen a disgusted face. And the findings held true for all sorts of aromas, including caramel and lemons, as well as the smell of garlic and even sweat. In fact, only the smell of feces could not be upvalued by a positive facial expression. Accountable for the different perception is a particular part of the olfactory brain, the pyriform cortex, which is activated before someone senses an odour. The pyriform cortex processes what we see and then creates an expectation about how something is going to smell. And this expectation then influences how we actually experience the smell. The fMRI data showed that the cells of the pyriform cortex became active even before a specific odour was in the air. While everyone's experienced static electricity at some stage, the aim has always been to try and get rid of the problem. However, scientists have looked at it from another way. They've now deliberately developed high-tech yarns that generate electricity when they're stretched or twisted. The research reported in the journal Science describes the so-called twistron yarns as capable of harvesting energy from the motion of ocean waves or from temperature fluctuations. The yarns are made from carbon nanotubes, hollow cylinders of carbon 100,000 times smaller in diameter than a human hair. First, scientists twist-spun the nanotubes into high-strength lightweight yarns. To make the yarns highly elastic, they introduced so much twist that the yarns coiled like an over-twisted rubber band. In order to generate electricity, the yarns needed to first either be submerged in or at least coated with an ionically conducting material or electrolyte. Mind you, that could be as simple as a mixture of ordinary table salt and water. This causes the yarns to act like supercapacitors. When a harvester yarn is twisted or stretched, the volume of the carbon nanotube yarn decreases, bringing electric charges on the yarn closer together and increasing their energy, which in turn increases the voltage associated with the charge stored in the yarn, and thereby enabling the harvesting of electricity. Scientists found that by stretching the coiled twistron yarn 30 times a second, they could generate some 250 watts per kilogram of peak electrical power when normalized to the harvester's weight. It means a twistron yarn weighing less than a housefly could power a small LED which lit up every time the yarn was stretched. Researchers also sewed twistron harvesters into a shirt, and normal breathing was enough to stretch the yarn and generate an electrical signal demonstrating its potential as a self-powered respiration sensor. And finally for now, looks like humans on the Italian peninsula have been making wine far longer than previously thought. The findings, reported in the Microchemical Journal, indicates Italian winemaking dates back to at least the early 4th millennium BCE. The results are based on chemical analyses of ancient pottery remains from a large storage jar. Traditionally, it's been believed that wine grape growing and wine production developed in Italy around the Middle Bronze Age between 1300 and 1100 BCE. But when archaeologists conducted chemical analysis of residue on unglazed pottery found at a copper age site off the southwest coast of Sicily, they discovered tartaric acid and its sodium salt, which occur naturally in grapes and the winemaking process. The authors are now trying to determine whether the wine was red or white. You're listening to Space Time. I'm Stuart Gary. And that's the show for now. You can subscribe and download SpaceTime as a free twice-weekly podcast through iTunes, Stitcher, Bytes.com, Pocket Casts, SoundCloud, YouTube, Audio Boom, your favourite podcast download provider, or direct from spacetimewithstuartgary.com. The show's also broadcast coast to coast across the United States on Science 360 Radio by the National Science Foundation in Washington, D.C., around the world on TuneIn Radio, and as part of Virgin Australia's in-flight entertainment. If you want more Space Time, check out our blog where you'll find all the stuff we couldn't fit in the show, as well as loads of images, news stories, videos, and other things on the web I find interesting or amusing. Just go to spacetimewithstuartgary.tumblr.com. That's all one word and in lowercase, and that's Tumblr without the E. You can also follow us through @StuartGary on Twitter, @SpaceTimeWithStuartGary on Instagram, and on Facebook, just go to www.facebook.com/Spacetime with Stuart Gary. Spacetime is brought to you in collaboration with Australian Sky and Telescope magazine, your window on the universe.
You've been listening to Spacetime with Stuart Gary. Subscribe at iTunes, Stitcher, Pocket Casts, or Audio Boom. This has been another quality podcast production from Bytes.com.